Okay. This is linear algebra, Math 313 at Lehman College. And we have a very intense 4 weeks. Semester is squeezed into 4 weeks, which is 15 days, 4 days a week, but 1 day is no school for Juneteenth. 1 day is the final. So there are 14 weeks of classes. The usual semester is 14 weeks, which means every day is a week's work. So it's hard, and you have to do a lot of work every day to keep up. So I'm going to follow in the lectures my notes, and the textbook that is posted on Blackboard is a secondary source. It's always good to read more than one source for the material you're trying to learn. So the primary source is my lecture notes, which are posted on Blackboard. And the secondary source is the textbook, which has been up for some time. So let's start. So chapter 1 in the notes is on linear equations and vector spaces. And section 1.1 is something that you've seen before, trying to solve one linear equation. Linear algebra begins with the study of linear equations. So you might have an equation like 2x equals minus 9. And there's a solution, x is minus 9/2. Or you might have an equation 4x plus 7y equals 5. And this equation will have probably more than one solution, in fact, infinitely many solutions. For example, one solution would be, I don't know, x equals 5/4, y equals 0. Or x equals 3. If x is 3, this is 12. So 7y has to be equal to minus 7, so y equals minus 1. So these are two different solutions of this equation. And of course, there are many, many more. In general, an equation in n variables looks like this. The letters we choose for the variables are up to you. A1, x1, this is a typical way, A1, x2, A2, x2, up to AN, xn equals B. So this is the standard form, or a standard form, of one linear equation in n variables. You don't have any variables squared. It's not a quadratic equation. You can have more than one variable, but every variable occurs alone or by itself, or doesn't occur at all. The right-hand side has no variables. And we say this equation is homogeneous if the right-hand side is 0 and inhomogeneous, which means just not homogeneous, if the right-hand side is different from 0. So these are both inhomogeneous equations. And the letters you use for the equations are up to you. You could have an equation like 3x1 plus 2x2 equals 7, or you might like to write the variables as x and y. Again, it's the same equation, it's just choice of a different letter for your variables. And we use sigma notation. This is a capital Greek letter sigma, and using sigma notation, which you've certainly seen in calculus, you would write this as summation sigma. J goes from 1 to n, a sub j, b sub a sub j, x sub j equals b. So this is the same equation as this using this more concise notation. So what we call a solution of an equation, summation aj xj equals b, j goes from 1 to n, is an n-tuple. That just means n real numbers, x1, x2, up to xn, such that when you plug in the numbers and you compute summation aj xj, you just get the number b. And we usually write the solution in this form as a column, x1, x2, going down to xn. So this is the standard way to write the solution of a system, and this is called a column vector. So this is purely notational. This is a column vector. We call it an n-dimensional column vector because they're n numbers. So if you had the example we just looked at, 4x plus 7y equals 5, one solution is the column vector, x equal 5/4, y equals 0. Another solution is x equals 3, y equals -1. So we write the solutions of this equation in the form of column vectors. And you should get in the habit of doing this as soon as possible. And just as notation, summation a sub j x sub j equals b, we call this a zero equation if all the coefficients of the variables are 0. And if b is 0, then you have the homogeneous zero equation, and every vector is a solution. If b is not 0, no matter what numbers you choose for the x's, you're always going to get a 0 on the left, and you'll never get b. So the inhomogeneous zero equation has no solution. The homogeneous zero equation has every vector as a solution. And again, there's a lot of terminology you have to learn. The set of solutions of an equation is called the solution space. And the set of solutions of a homogeneous equation, so if the equation is homogeneous, another name for the solution space is a hyperplane. Hyperplane. Again, I don't worry too much that my handwriting is not good, because everything is in the lecture notes, which are printed and on Blackboard, and you can follow everything there, and everything there is beautifully legible. So let's go back and look at that simple equation we had at the beginning. 4x plus 7y equals 5. And 3 minus 1, that vector, is a solution. because 4 times 3 plus 7 times minus 1 is 12 minus 7 is 5. That's a solution. In general, if you fix any x, you can solve this equation for y. Then, so let me do it just step by step in the beginning. 4x plus 7y equals 5. So 7y is 5 minus 4x. So y is 5 over 7 minus 4 over 7x, or 5 minus 4x over 7. So if you give me any number x, and I define y by this equation, I get another solution. And every solution is of this form. So for all x, we get a solution. So if we let xy be the vector x, and what is y? Y is 5 minus 4x over 7. This is a solution for all x, and this is the general solution of this equation. So if we're trying to study this simple linear equation in 2 variables, the set of all solutions, every solution is of this form. If the first coordinate is x, the second coordinate must be 5 minus 4x over 7. Well, we don't have to look at equations in just 1 or 2 variables. We can look at equations in any number of variables. For example, 3x minus 2y minus 5z equals 17. So that's one linear equation in 3 variables. Now, if you give me any x and y, I can always find a z that solves this equation. Because for any x and y, for any solutions of this equation, if I just rewrite this, 5z is minus 17 plus 3x minus 2y. I just rearrange that equation. So z is minus 17 plus 3x minus 2y over 5. So for any vector, if I take any numbers x and y and make them the first 2 coordinates of a vector, if I let z be minus 17 plus 3x minus 2y over 5, this is a solution. So for example, if I let x equal 3 and y equals 6, what is z going to be? Z is minus 17 plus 3x minus 2y over 5. That's minus 17 plus 9 minus 2y minus 12 over 5. Minus 17 minus 12 is minus 29 plus 9 is minus 20 over 5. Oops, is that right? Minus 17 minus 12 is minus 29. Plus 9 is minus 20. Minus 20 over 5 is minus 4. So when x is 3, y is 6, z has to be 4. So the vector 3, 6 minus 4, this vector, if I plug it into this equation, we'll see that it works. Let's see. 3 times 3 is 9, minus 2 times 6 minus 12, that's minus 3. Minus 5 times minus 4 is plus 20. 20 minus 3 is 17, so this checks. Okay. So the takeaway so far is if you have a linear equation, homogeneous or not homogeneous, it has solutions. And the solutions we write as vectors. So there is some sort of vector algebra. Remember, a vector, an n-dimensional vector, is just a column in big parentheses of n numbers. And by vector algebra, I want to describe, first of all, how to add and subtract vectors. So if you have two vectors of the same dimension, they have to have the same number of coordinates. You can add them just by adding the coordinates. So if you had, for example, the vector 1, 2, 3, and the vector 4, 5, 6, and you add them, you add coordinates. 1 plus 4 is 5, 2 plus 5 is 7, 3 plus 6 is 9. And you divide subtraction in the same way by subtracting coordinates. So 1, 2, 3 minus 4, 5, 6. 1 minus 4 is minus 3. 2 minus 5 is minus 3. 3 minus 6 is minus 3. We just get that vector. I should also add there's the vector, all of whose coordinates are 0, is called the 0 vector, which is usually written as a bold-faced 0. And that's the vector where every coordinate is equal to 0. And this property of adding vectors satisfies, or this definition of vector addition satisfies certain properties. It's associative. That means if you take a vectors x, y, and z, if you add x plus y, you get a vector, and you add that to z, you get another vector. But that's exactly the same as if you took y and z and added them and then added x to that. So this is called the associative law, or the associative rule for addition of vectors. Vector addition is associative. And it's also what is called commutative. X plus y is the same as y plus x. If you had 2, 3 plus 7 minus 1, that's 9, 2. If you add in the opposite order, it's still 9, 2. So the order in which you perform addition doesn't matter. And you have an identity vector, 0. The 0 vector plus any vector x is equal to x, right? Because if you have, for example, 0, 0, 0 plus 2, 3 minus 7, that's still 2, 3 minus 7. That's the 0 vector. And if you take the vector x, x1, x2 down to xn, we define minus x to be the vector where you just take the negative, the opposite, of all the coordinates. And then you can check that x plus the vector minus x is always the 0 vector. So 2, 3 minus 7, if you change the sign of each coordinate, you get minus 2, minus 3, plus 7. And when you add, everything cancels and you get 0, 0, 0. So this is the operation of vector addition. There's also an operation that is called scalar multiplication. And in linear algebra, Another word for number is a scalar. So number and scalar are synonyms in this subject. So scalar multiplication is when you multiply a vector by a scalar or by a number. So for example, if you had the vector 2, 3, minus 7, and you multiply by 5, you get 10, 15, minus 35. In general, if you have the vector in n dimensions, x1 up to xn, and you want to multiply by a scalar c, you just multiply each coordinate by c. That's the operation of scalar multiplication. And scalar multiplication has very nice properties. For example, you have the distributive laws. If you take two scalars, c plus c prime, and you multiply by a vector x, that's cx plus c prime x. If you take two vectors x and y, you add them and then multiply by c, that's the same as multiplying x by c, multiplying y by c, and then adding them. So these are called the distributive laws, or scalar multiplication and vector addition. And using these rules for adding and multiplying vectors, we have a very elegant way to describe solution spaces of linear equations. So let's go back to the equation we looked at already, 4x plus 7y equals 5. If you solve this equation for y, you get y is minus 5 plus 4x over 7. So the solution space of this equation is all vectors x, y, where y is minus 5 plus 4x over 7. I can write this like this. This is x, and this is minus 5/7 plus 4/7 times x. I can think of x as, let me just write it like this to make it sort of very clear, 0 plus x. Right? Add 0 to any number, it doesn't change it. But if I write it in this form, it looks like the sum of two vectors. This is the sum of the vectors 0, minus 5/7, plus x, 4 over 7x. Oops, I wrote this backwards. If I'm solving this for y, y is equal to 5 minus 4x over 7. Got the sign wrong. So this is 5 minus 4x over 7. So let me make sure I do this right. So this is 0, 5/7 and x minus 4/7 x. And x is the same as 1 times x. So I can think of this as the scalar multiplication. So this is my 0, 5/7. Plus, if I take the vector 1 and minus 4 over 7, and I scalar multiply that by x, this is what I get. So my solution vector xy is of this form. It's this vector plus any scalar multiple of this vector. So the solution space is all vectors that can be written in this form. So this is a very good exercise in vector algebra, let me do another example. Here's an equation again we looked at a moment ago. 3x minus 2y minus 5z equals 17. And we solved for z, we got z is equal to minus 17 plus 3x minus 2y divided by 5. So the general solution of this equation is x, y, z equals what? Choose any number x, choose any number y, but once you choose x and y, z is determined. Z is minus 17 over 5 plus 3 over 5x minus 2 over 5y. And just to make this sort of super clear, x, right? My first coordinate is x. My second coordinate is y. I can write x as 0 plus 1 times x plus 0 times y. That's equal to x. And y is 0 plus 0 times x plus 1 times y. And when I do that, I can write this vector as a sum of 3 vectors. 0, 0, minus 17 over 5, plus 1 times x, 0 times x, 3/5 times x, plus 0 times y, 1 times y, minus 2/5 times y. And each of these is a certain vector, scalar multiplied by x or y. So this is 0, 0, minus 17 over 5, plus x times the vector 1, 0, 3/5, plus y times the vector 0, 1, minus 2/5. So for this linear equation, it's an inhomogeneous equation in 3 variables, x, y, and z. The solution space is all vectors that can be represented in this way. And every vector of this form is a solution. Okay. Any questions about that? So let's continue. This is section 1.2 on vector subspaces and affine subspaces. So remember, an n-dimensional vector is just a column of n numbers in these big parentheses. And by Rn, this is the set of all n-dimensional vectors, where the numbers x1 up to x2 up to x sub I, these x sub i's are called the coordinates, are real numbers. And we call our n a vector space. It's the most important example of a vector space. We'll see later with a more general definition of a vector space. But we have the vector space Rn. And you can think of this as, well, what's R1? That's just one number. You can just think of that as the real line. R2 is all pairs of numbers. You can think of that as the plane. It's more common to write the variables as x and y, but x1, x2, or xy, it doesn't matter. R3 is all triples, or you can use the letters x, y, and z. That's just three-dimensional space. And R4 is harder to picture, and there's no way I can draw it, but it's four-dimensional space and so forth. So Rn, for every positive integer n, we have the vector space Rn. And sitting inside Rn, a subset W of Rn is called a subspace, or it's sometimes just to emphasize, it's called a vector subspace if it satisfies the following three properties. First, the zero vector is in W. Second, it's closed under vector addition. That means if W1 and W2 are vectors in W, then the sum, W1 plus W2, is also in W. This symbol means in, is in. This element, this vector, is in the set W. So a subset W is called a subspace if it contains the zero vector. It's closed under vector addition, and it's also closed under scalar multiplication. So that's what a subspace is. And there are lots of very simple subspaces. For example, suppose I let W be the set of all vectors of the form x comma x. So if you think of this in the plane, R2, so this is a set W contained in R2. This is a set of two-dimensional vectors. So here's the plane R2, and we're looking at the set of vectors where the second coordinate equals the first coordinate. That's just the line y equals x. So R2 is this whole infinite plane, and W is just the straight line y equals x. So this line through the plane, through the origin in the plane, is a very nice example of a vector subspace. And vector subspaces have nice properties. In general, suppose we have vectors x1, x2, up to x, and let me use a different subscript, xk. So these are k vectors in Rn. And suppose I take C1, C2 up to C sub k, scalars, which just means numbers. So I can take the vector x1 and multiply it by C1. I can take the vector x2 and multiply it by C2. I can take the vector x3 and multiply it by C3. And I do that for every vector. Finally, I get the vector xk multiplied by ck. And then I can add. You can add pairwise starting from the left. Vector addition is a binary operation. You got two vectors. So this plus this is a vector. And add c3, x3, and so forth, up to cn, xn. So this is a new vector in Rn. And this kind of vector is called a linear combination of the vectors x1 up to xk. So this is another new and important definition. Linear combination of vectors, x1 up to xk, is another vector which you get by multiplying each of the original vectors by a scalar and adding. That's a linear combination. And one can prove that a set W contained in Rn is a subspace if and only if there's something in W. W is not, this symbol means the empty set. That's the set of vectors with no vector in it, the empty set. So if W is not empty, it means there's some vector in W, and W is closed under the operation of taking linear combinations of its elements. And conversely, if x1, x2 up to x sub k is any set of vectors in Rn, non-empty set, there's at least one vector, then the set, call it W, of all linear combinations of vectors, let me call this set S just to give it a name. So S is a set of vectors. The set of all, let me not call it W, the set of all linear combinations of vectors in S is a subspace, which is called the subspace generated by S. Okay. There's a lot of fundamental definitions and terminology that you need to learn quickly in linear algebra. There's a very useful symbol called the Kronecker delta. So this is a lowercase Greek letter delta, and we give it two subscripts, I and j. And when you find delta ij to be equal to 1, if I is equal to j, and 0 if I is different from j. So for example, delta 3, 3 is 1, but delta 3, 4 is 0. Because here the two subscripts are the same, and here the two subscripts are different. That's the Kronecker delta. So here are some special vectors let me just start with R2. So R2, we have the vector defined to be as follows. E1 is the vector 1, 0, and E2 is the vector 0, 1. In R3, we define three special vectors, E1, E2, and E3. E1 is 1, 0, 0. E2 is 0, 1, 0. And E3 is 0, 0, 1. In fact, I could write these concisely using the Kronecker delta. For example, in this case, for I equal 1, 2, and 3, E sub I is the vector whose coordinates are delta I1, delta I2, delta I3. Plus if I equals 1, this is 1, 0, 0. If I is 2, this is 0, 1, 0. If I equals 3, this is 0, 0, 1. And in general, in Rn, we can define E1 to be 1 and then all the rest zeros. E2 has a 1 in the second coordinate and everything else is 0 and so forth. E sub n has zeros in all the coordinates but a 1 in the nth coordinate. And again, if you want a consistent way to write this, you could say that E sub I, the ith vector of this special set, has coordinates delta I1, delta I2, down to delta In, because it's only when the second coordinate is equal to I that you get a 1 that is in the ith coordinate. This is 1, and every other coordinate is 0. And in fact, in terms of these special vectors, there's a very neat way to write a general vector. If you take x1, x2, x3 into xn, I could write this as x1, 0, 0, down to 0, plus 0, x2, and then everything down to 0. And then 0, 0, x3, and then everything else is 0. Up to finally 0, and then the last coordinate, xn. So I'm just writing this n-dimensional vector as the sum of these n vectors. But I can take this x1 out. I can write this as x1 times the vector 1, 0, 0. And this is x2 times the vector 0, 1, 0. And this is x3 times the vector 0, 0, 1, and then zeros, and so forth, down to xn times 0, 0, 1. So another way of writing this is using this special vectors. This is x1, e1. I just write this is boldface, plus x2, e2, plus x3, e3, up to xn, en. So this is just an extremely useful standard way to write a vector. You can write it as a linear combination of these special vectors, E1 up to En. So I defined a vector subspace, and it's a very important fact that the set of solutions, or the solution space of an homogeneous linear equation in n variables is a vector subspace of Rn. So what does our equation look like? It looks like a1 x1 plus a2 x2 dot 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 an xn equals b. And let W be the solution space. So if x1 down to xn is in W, and if y1 to yn is another vector in W, then you write these, then a1 to xn up to, and this is equals b. And similarly, if I plug in the numbers y1 up to y1, y1 up to yn, I would get a1 y1 plus a2 yn up to an yn equals b. And if I take these two solutions and I add them, I get a1 x1 plus y1 plus a2 x2 plus y2 plus an xn plus yn equals b. So that means that x1 plus y1, x2 plus y2, xn plus yn, this vector is in W. But this vector is just the sum of the vectors of the x's and the sum of the vectors of the y's. So if you have two solutions of this, I'm sorry, this is a homogeneous equation. This equals 0. This 0 plus 0 has to be 0. And if you add 0, if you add these two equations, you get 0 plus 0 equals 0 on the right-hand side. If you take the set of all solutions of a homogeneous linear equation, you can add them. Perform vector addition, you get another solution. So the set of solutions is closed under vector addition. And if I also multiply through by c, I still get 0, because c times 0 is 0. But c times a1 x1 up to an xn is the same as a1 times cx1. I'm just distributing across an cxn. So the vector cx1 down to cxn is the solution. This is c just times the vector x1 up down to xn. So if the vector of x is the solution, any scalar multiple of it is. So this set W is non-empty, because the 0 vector is always a solution of the homogeneous equation. And it's closed under vector addition and scalar multiplication. So we have the following theorem. It says, this is the solution space of a homogeneous linear equation in n variables is a vector subspace of Rn. Okay. So in two variables, like if you have an equation ax plus by equals 0, what's the solution space? Solve for y. Y is minus, if b is different from 0, minus a over bx. It's just a line through the origin. The slope minus a over b. That's my solution space W. And typically for equations in two variables, the solution space of an equation is always a line through the origin in the plane. What about a line that's not through the origin? It's sort of like you take this line through the origin and you push it up by a fixed amount. So let me define the translate of a set W contained in Rn by a vector V in Rn is simply the set, which I'll denote it by V plus W, which is the set of all vectors V plus little w as W runs through all the elements of the set W. So you have a set W. If you add V to every element in W, you've translated W by the vector V. And what is called an affine subspace is a translate of a subspace. So in the plane, if you take a line through the origin, that's a subspace. Any translate of that, which is any parallel line, is an example of an affine subspace. And these come up in linear algebra in many important places. In particular, we have a new theorem which says the solution space of an inhomogeneous equation is an affine subspace. So we already saw that in the case of, what was that nice equation we have been looking at the beginning? 4x plus 7y equals 5. So if you solve this equation for y was equal to 5 minus 4x over 7. So the solution space looked like x, y, x, 5 over 7 minus 4 over 7x. That was 0, 5 over 7, plus x times the vector 1 minus 4 over 7. The set of all vectors, x times this fixed vector, that's a vector subspace, and I'm translating it by this vector. So we get an affine subspace. The solution space of this inhomogeneous equation is this affine subspace. And yeah. Okay. So I think I'm going to stop at this point. I've just covered a lot of material, I think, exactly what I wanted to cover. So in the lecture notes, this is sections 1.1 and 1.2 of chapter 1. And there's homework from these that is due on Wednesday. And I would encourage you to really study the notes very, very carefully and try and do all the homeworks. Starting tomorrow, in addition to this lecture 9 o'clock, I'm also going to have a kind of office hour problem session on Zoom in the afternoon, when anyone who wants can log on and ask questions about either the material in the lectures or the material in the notes or the homework problems. And I will post on Blackboard the hours of the problem sessions for the rest of the week. Okay.
Excuse me, Professor.
Any questions before we stop for the morning? Yes, go
I
ahead.
have a question.
Yes, please.
I see where I can submit the homework, but I can't see the problems, the homework. How I can find it?
The homework, so there's a homework schedule that's on Blackboard for this week. And it says what the problems are, and they're the problems in the lecture notes. So in section 1.1 and section 1.2, there are problems. Let me just pull something up to show you. So let me see if I can share my screen. So do you see this that says homework schedule?
Yeah.
So this is on Blackboard already. And this is the assignment that's due Wednesday. And this is the assignment that's due Friday.
Okay, thank you.
Okay. Other questions? Okay.
Yeah, another question. So
Yeah, go ahead.
we have to write it in a paper and we can send it as a file.
So again, all of this is explained in the information sheet that's on Blackboard and that I also emailed out to everyone. So you have to be able to, this is for the homework and for the exams. You have to have access to a printer that you can scan your pages and convert them to a PDF file. And you upload the PDF file to the assignment section of Blackboard. So for every homework, there's a specific site in assignments where you upload that particular homework. And that's what you do. So you write out the solutions to the problems by hand, you convert it to a PDF file, and you upload the PDF file to Blackboard.
Okay, thank you.
Sure. Other questions? Okay. Good. Looks like a beautiful day. Enjoy the day, and I will be back 9 o'clock tomorrow. Bye, all.
Thank you. Bye.